I wanted to briefly explain the connection between confidence intervals and hypothesis test. We know that both of these things are ways that we can do inference. Okay, they're both types of inference that we can do. And I just wanted to show you, with the aid of a couple of examples, what the connection really is between those two different types of inference. So, taking a 95% confidence interval is really akin to doing a two-tail hypothesis test where the alpha level would be 0.05. Okay, so the alpha equals 0.05 and the 95% confidence interval, you can kind of think of those as complementary to each other, so they add up to 1. Same way with a 90% confidence interval, that would be akin to doing a two-sided hypothesis test where the alpha is 0.10. And likewise, a 99% confidence interval is akin to doing a two-tail hypothesis test where the alpha would be 0.01. All right. So let's look at this in the context of an example. Okay, so let's say that we're talking about a means problem. All right, and let's say, for instance, since we've been talking about it just before, and it's a good use of example, let's say we're talking about an IQ problem. Okay, so let's say we take a random sample of adult IQs. Let's just say we're talking about, I don't know, 49 people. All right, and let's say I measure their IQs, and the mean IQ is, let's just say, 108. All right, and let's say I want to construct a 95% confidence interval for that. Okay, and let's just suppose that the standard deviation of that is, I don't know, let's just call it maybe 5 points. If I'm going to do a confidence interval, let's assume that we meet all of our conditions. Okay, central limit theorem. All right, that's cool about that. So I got the normal condition, and there's more than 490 people in the U.S. So that would be good, and it was a random sample. So we met all our conditions. So if I take a confidence interval, x bar plus or minus, okay, since we don't know sigma, we would be using a t star, okay, times the standard error. So the standard deviation of our sample, or we can call that s of x, divided by the square root of n. So in this case, since n equals 49, the degrees of freedom would be 1 less than that. It's 48. All right, so we would be doing, how can I figure out what the t star is? I can be using my calculator. And if I take a 95% confidence interval, that middle part is 95%. So there's 2.5% left in each tail. And this would be the location of my t star, my t critical. All right, so if I go into my calculator here, I go second distributions, and we want to do inverse t. This is a t distribution. The area is actually 0.975, so we have to add that 2.5% to this 95%. Okay, the degrees of freedom is 1 less than the sample size, so 49 minus 1 is 48. I would paste it, and I would get a t star of 2.0106. Okay, so the t star is 2.0106. And in my calculator, I'm just going to store that as t. All right, so if I want to start writing this out, I have an x bar plus or minus, oops, let's actually fill in the numbers. We have 108 plus or minus 2.0106 times the standard deviation, which we said was 5, over the square root of n, which is 49. All right, so if I'm looking at this, all right, let's take this 2.0106 and multiply it by fraction 5 over the square root of 49. So 1.436. If I round it. All right, and this thing right here, that total value would be known as the MO, or the margin of error. Okay, so if I take 108 and subtract that number, okay, let me just store this as alpha real quick. So I take 108 minus that number. That's the lower part of the interval. Okay, and if I do 108 plus that number, gives us the upper end of the interval, 109.4362. Okay, so basically my mu has got to be somewhere from this value to this value. All right. So we would say something to the effect of, we are 95% confident that the true mean IQ of adults in the US is between 106.56 and 109.44, if I just rounded two places. All right. So that's the confidence interval. Okay, now, what about if someone said, or someone told you that the mean was 100? Okay, suppose someone said mu was 100. Would you believe them based on your results here? Hopefully you would say, no, I don't believe you because I'm 95% confident that mu lies somewhere between these two values. Okay, and we can confirm those real quick if you guys want to look at that. If we go over to test here, if I go down to t interval, number 8, I'm going to input stats. My x bar was 108, my standard deviation was 5, my sample size was 49, my confidence level was 95. So calculate it out, and we get exactly the same answer that we got there. So if someone told you the true mean was 100, since 100 is not inside of this range of values, we would say no, that's not true. Okay. So let's compare that same type of problem to a hypothesis test, where the alpha equals 0.05. So the first assertion is that the mean equals 100, basically the same thing that the person claimed down here. And the alternative would be that it's different. Okay? Because when you compare confidence intervals and hypothesis tests, you have to have a two-tailed hypothesis test. Okay, so what we do is we assume that 100 is right down the center. And remember that this normal curve is the sampling distribution. Okay. Now, what was our actual x bar? What was our sample mean? It was 108, which puts it way over here, puts it to the right. Okay. And again, let's assume all of our conditions are met, and let's just go to calculations. So when we go to calculations here, we have to find the test statistic, or the t-value. Okay, so how do we find the t-value? We take the sample statistic minus the hypothesized parameter, and we divide it by the standard error. Okay. So in this case, to find this, we would take our 108 minus what we think the mean is over Sample standard deviation is 5, and the sample size is 49. So if we do this, it's going to be 8 divided by 5/7. Okay. If I do 8 divided by 5/7, it's 11.2. It's a huge t-value. Okay, it's a huge, huge t-value. So 108, remember that's an x-bar. The t-value associated with that is 11.2. So if this really was the true mean, we would just observe a sample mean that's 11.2 standard deviations above the center. So when you actually figure out what the p-value is, what the probability of that is, I would hope you would think that that would be relatively low, since it's 11 standard deviations above. Now, you got to be careful here, because this is a two-sided test. Okay? And because it's a two-sided test, after we find this area, we actually have to double it. Okay? We have to double it, just like if this was, it was 8 away on this side, it's got to be 8 away on this side. So it's 92 there. Okay, it's 8 less. Okay, which would correspond to a t-value of, a t-statistic of negative 11.2, because the center would just have a t-value of 0, because we're normalizing that. Right, so how do I find the p-value? I'm going to find this area, and then I'm going to double it to get that. So on the calculator, okay, there's a way we can do this. We can go to our distributions, and we can go TCDF, which means the t distribution, and C stands for cumulative. Okay. So for instance, if I wanted to find this area right here, the t-value starts at 11.2, it goes up to infinity, right, and the degrees of freedom is still 48 here. Now, that's tiny. That's times 10 to the negative 15th. And you still got to double it because we have area on the left as well. That's symmetrical. All right. So the p-value is actually 5.45 times 10 to the negative 15th, which for all practical purposes is nothing. Okay, it's like a decimal point, then 14 zeros, and then a 5. So I don't really care what alpha level we pick, but since we're going to make it match over here, that's 95%, so this is 5%. Okay, obviously here, when we get to our decision, the p-value is much, much, much smaller than the alpha. This is essentially 0, and that's still less than 0.05. So because the p-value is less than or equal to alpha, our decision is to reject HO. All right. So we do not believe that's true. Just like we didn't believe that 100 was the true mean, because 100 is not inside this interval. Okay, so there's a connection here. If someone tells you, if the number that someone tells you is not in the interval, that's like rejecting that as a null hypothesis. So that's the comparison between these two things. Okay, rejecting the null hypothesis is like saying, no, I don't believe that, for the same reasons that over here 100's not in the interval. Okay, now we would conclude this and say there is sufficient statistical evidence at the alpha equals 0.05 level to conclude that the true mean adult IQ, adult US IQ is not 100. So that's how we would conclude. So this was my decision, that was my conclusion, this was these were my statements, and these were my calculations, and we're just assuming that all the conditions are met. So hopefully you see that linkage. Now, What about if 100 would have been inside this interval? If 100 was inside this interval, then the result over here, okay, this test statistic would be much less than 11.2. It would fall much closer to the center. All right, and the p-value would actually be more than 0.05 in this case. Okay, so if 100 was in the interval, then over here, the connection would be, the p-value would be greater than alpha, and we would fail to reject. So we would still have to believe that that was possible. So that's the connection between confidence intervals and hypothesis tests with means. Okay. So just to kind of summarize it one more time. All right, if the parameter is not in the interval, that's akin to rejecting the null. If the parameter that someone tells us is in the interval, inside the interval, that's like failing to reject H naught. Let's do one more example here, but let's do it for a proportions problem. Okay. So let's just suppose that suppose I'm taking a sample of something and I get a p-hat of, I don't know, I'm trying to think of a decent example here. All right. What proportion of students in the school are in the National Honor Society? What proportion of students in the school are in the National Honor Society? Okay, so we take a sample. Let's say we take a sample of, I don't know, 35 students. And let's say that 15 of them are in the National Honor Society. Okay? This is going to be our sample statistic that's going to be used as a point estimator for rho. Okay, because I want to know about rho. I want to know about the population proportion. Okay, so if we did let's just do a 90% confidence interval in this case. All right, to estimate rho. Okay, so if I did a 90% confidence interval, and let's just do a condition check real quick here. All right, so random, let's assume that the 35 people I picked for the sample, I chose at random. All right, independent, and it's greater than 10 times 35. All right, so that'll be 350. At least at my school, there's almost 400 students, so that's checked off. And the normal condition, all right, since we don't know rho in a confidence interval, we're going to take n times p hat and make sure it's bigger than 10. We're going to take n times p hat, or n times 1 minus p hat, and make sure that's also greater than 10. So n times p hat would be the number of successes, 15. All right, and n times 1 minus p hat would be the number of failures. So in this case, that's 20. Those are both bigger than 10. So we're okay there. Now when we get to our calculations, we take p hat plus or minus, but we're going to use a z star here, okay, because it's a proportions problem. All right, times the standard error of that statistic, so that'll be p hat 1 minus p hat all over n. All right, so I would be taking, let's think about what these are. The p hat is 15 out of 35. Okay, so as a decimal, I think that's the same as 3/7. which is about 0.4285, 86 if you round, sorry. All right, the sample size is 35. So we got our p-hats, we can put those in. All right, we got our n, now we got to figure out z star. So how do I figure out z star? I'm going to draw my bell curve, my normal curve. It's a 90% confidence interval, so 90% falls in the center, and there's 5% left in each tail. Okay, so z star is right there. All right, so to calculate z star, we go to our trusty calculator, and we go inverse normal, but the area is actually 95 because the calculator does a left tail area. This 5% plus that 90. All right, and we leave those alone. We paste it, and there's our z star, 1.645. Okay, I'm just going to store that as z. Let me do that p-hat again, and let's store that one as p. So to calculate this interval, take p-hat, 0.4286, plus or minus the z star, which is 1.645, times a big square root of 0.4286, 1 minus 0.4286, all over 35. Okay. So let's figure out what that margin of error is. Okay, I'm going to take my z times big square root Okay, I called my p-hat p in my calculator, and 1 minus the p-hat over the sample size, which was 35. Okay, so that's the margin of error, 0.1376. So to get our interval, we take the p-hat minus, again, this is the margin of error, the total margin of error. Right. So let me just store this as another letter. So I can do p minus a and p plus a here. Okay, so this is a very, very wide interval. You might ask yourself, why is this so wide? Well, we only sampled 35 people, that's why. 0.2910 if I round, 0.5662 if I round. Okay. So our conclusion is something like this. We are 90% confident that the true proportion of students in National Honor Society at this high school is between that value and that value, or you can express them as percents. So 29.1% and 56.62%. All right, so we think rho is somewhere inside that range of values. And that's where we think rho is. Okay, so if someone told you there's 50% of students are in National Honor Society, could you refute that? Well, let's ask ourselves, 50%, that number would be inside this interval. Okay, so if someone told me this, I couldn't statistically show that it could not be true. Okay, so since that number is inside that interval, I cannot refute that statement. I have to believe that statement at face value, because that is a possibility for rho. All right. So now let's come over here and let's do a similar hypothesis test, a similar two-tail hypothesis test. So the claim was that rho was 50%. Okay. And the alternative, what you would need proof of, okay, what you need evidence to disprove that it's different than 50%. Right. Now, so we go into this normal curve assuming that 0.50 falls down the middle. Again, these would be p-hats, because this is a sampling distribution of the p-hats. That's the sampling distribution of the p-hats. Now the conditions are very, very similar. Okay, the conditions are very, very similar, okay, but there's one big difference. All right, the random works exactly the same way. The independent works exactly the same way. But when we do the normal calculations, we do them very similar to here, but we don't use p-hat anymore. Okay, we have an assumed value of 50%. So here we would just do n times rho. That's what makes it a little bit different on the conditions. Okay, so here you would do 35 times 50%. Has to be greater than 10, which it is. I mean, it's 17 and a half. Half of 35 is 17 and a half. And 35 times 1 minus 0.5, well, 1 minus 0.5, it's just 0.5 again. Okay, so that condition is met too. I just want to give you the difference there. So a slight difference, just be aware of that. Now, let's actually jump into the calculations here. Now, our test statistic, since we're using a z-curve, the test statistic would be z. Okay, and it's similar to the last t we had. We're going to take our p-hat minus our hypothesized value. However, the standard error is a little bit different for the same reason we use rho here. Think about this. Over here, we didn't know what rho was, so we had to use p-hats in its place. We use p-hats in confidence intervals. But on hypothesis tests, we have to use the assumed value of the population proportion. Okay. So there's a slight difference there as well. Okay. So in this particular problem, we would take our p-hat, which we already found was 0.4286, okay, minus the assumed value, which is this, the hypothesized parameter, all over square root of 0.50, 1 minus 0.50, over the sample size, which is 35. So let's calculate that out. Remember that my sample proportion was right there, minus 0.5. So that's negative 0.0714 divided by. Okay, if I take 0.5 times another 0.5, that's a fourth. Okay, so we're 0.25. So I'm going to divide that by the square root of 0.25 over 35. So here it looks like the z-score is negative 0.8451. So our p-hat, so on this curve, on the sampling distribution curve, our sample value of 0.4286 would almost fall one standard deviation below the curve. This is almost -1, so it would fall right there. And again, now here for this particular alpha, okay, this alpha, since this is a 90%, we're assuming here that the alpha is 0.10 and alpha of 0.10. Okay, so we have to find the test statistic value. We found that right there, -0.8451. I'm just going to go ahead and store that as Z. Okay. Now we got to find the p-value, or the probability that we get a sample proportion that extreme. So I need to take this area, but I have to remember that I got to double it, okay, because this is a two-sided test. Okay. So if I'm thinking about the left tail area, I can go to normal CDF, and I can go from -infinity all the way up to my Z value. Okay. And these are Z-scores, so they're standardized already, so that's 0 and 1. We leave that there. Hit paste, hit enter. Now, that's the area of the left tail, okay, just about 20%. But since it's a two-tail, we got to double it, 0.398. When we're doing our calculations, we got to show either a formula for hypothesis test or the name of it. This would just be called a one proportion or a one prop z-test. So as long as you give the name of the test or you give the correct formula, you will get credit there. When they want you to give the test statistic value and they want you to give the p-value. Now, when we get to our decision here, our p-value is 0.398. That is greater than our alpha, which is 0.05. So our saying is when p is low, reject the HO. Well, the p is not low compared to the alpha. So I'm going to fail to reject HO. I don't have enough evidence. My sample proportion was not far enough away to believe that. Okay. So I have to continue to accept this 50% claim, just like I had to accept the 50% claim down here because 50% was in that interval. So my conclusion on the hypothesis test is something like there is not sufficient statistical evidence to conclude that the true proportion of this high school students there is not sufficient statistical evidence to conclude that the true proportion of this high school's students in NHS differs from 50%. Yeah, something like that. Have to believe this claim because 50% is in the interval. Have to believe this claim because the p-value was greater than alpha. So that's the connection between the two. Okay, whether you're doing a hypothesis test or you're doing a confidence interval, if you get asked a question like that, over in the confidence interval, we just have to look up to the interval. Is that value in the interval? If it is, okay, then I can't refute it. But if this would not have been in there, then I could say, no, I don't believe that it's 50%. Just like over here, if our p-hat was far enough away, if it was much further away from the center, Okay, the p-value would have been much lower, and then it would have been less than alpha. If it was less than alpha, then I could reject the null hypothesis, and I could say it's different than 50%. So there's the connection again. Just be aware of the slight differences in that condition and that condition. Okay, and the standard error as opposed to the standard deviation of the hypothesized parameter. So slight differences in formula. Slight differences in formula. So I hope that shows you a little bit about the connection between the two. Just remember, if you think through it, it's not that bad. Just pull up this other page again real quick. All right, taking a 95% confidence interval is just like doing a two-tail hypothesis test with the alpha of 0.05, so on and so forth. You should reach the same conclusions, okay, doing either type of inference, confidence interval or hypothesis test. So I'm going to stop the video there.